We're going to begin today with looking at three linear systems, and we're going to look at the possible results for the solution set of a linear system. And that comes into zero. That being, linear systems can have solution sets that have zero solutions, one solution, or infinitely many solutions. So we're going to go all the way back to elementary algebra to remind ourselves what we're looking for, because we're going to be looking for the same thing even when we have 10 equations with 12 unknowns. We're going to be looking for the same thing: 0, 1, or infinitely many. So set your Wayback Machine to elementary algebra and let's take a look at these linear systems. In the linear systems, notice all three of them have an x minus y equals 1. So let's solve these systems by graphing so that we can visualize what's going on. And I'm going to start by looking at x minus y equals 1. And I'm going to graph this by making a table of values, because I only need 2 because it's a linear function. If x is 0, then y is -1. So I'm going to put the point 0, -1. And if y is 0, x is equal to 1. So I'm going to put the point 1, 0. So we have a line with a y-intercept of -1 and a slope of 1. So I'm going to put more points. I'm going to realize that I did not bring a straight edge, so I'm just going to draw a wiggly line connecting the dots, and we're going to pretend that it's a nice straight line. There we go. So that's the equation: x minus y equals 1. Now I'm going to graph the other line, and we're going to look for the intersection. Some of you can already see it. This line does not have a slope of +1, so we're going to get an intersection somewhere. Let's look at this second equation and write it in the form, let's solve for y. Let's write this as y is equal to -3 over 2 x plus 8 over 2, which is 4. So I'm going to plot the point 0, 4. And I'm going to go in the direction of -3/2. So I'm going to go -3 in the vertical direction and 2 in the horizontal direction. And so here would be the other line. And we can see that the graphs cross at the point, looks like 2, 1. And so that will be our solution to the system. We have exactly one solution to this system. All right. We want to make sure that we say exactly one solution, because when I say one solution, we mean exactly one solution. So if you have $5 in your pocket, if I say, do you have $1? You say yes, because you have $1, at least $1. But if you have a $5 bill in your pocket and I say, do you have exactly $1? Then the answer is no. This is math class. We're speaking a very precise language. When I talk about one solution, we mean exactly one solution. We'll say a unique solution. But this was not difficult. We should start off with a nice, easy problem. It's the first day after all. We'll just kind of like ease into this one. Let's look at the second system, where I still have the line x minus y equals 1. I'm just going to copy what I did before, and now you can see why I chose to use this line over again, so I wouldn't have to graph another one. This is called teachers are lazy. So there's the line x minus y is equal to 1. I forgot to label my previous line as 3x plus y. Sorry, plus 2y equals 8. So in this system, I've got the line minus x plus y is equal to 1. So I'm going to graph this one in the same way I did the last one. I'm going to solve for y. And so I have a slope of 1 and a y-intercept of 1. So this line is going to start off at 0, 1, and have also a slope of 1. So what we end up with is this system represents parallel lines. We're looking for where these lines intersect to be the solution to the system, but these lines do not intersect. So we say there are no solutions. The lines do not intersect. So you can probably guess what's going to happen in the third example, because it's 0, 1, or infinitely many. This last one, I wonder what's going to happen. I use the same line because rule 1, teachers are lazy. And so I'm going to plot that line again. So I have a x minus y equals 1. Oops. I kind of gave it away there, little spoiler. I started to write the second equation because the second equation is really the same as the first equation. It says the same things. So there's the line x minus y is equal to 1. And if I plot the second line, I'll do the same thing. This is elementary algebra style after all, so I'm just going to solve for y. Y is equal to x minus 1. And we'll notice we get the same line. We're going to have a y-intercept at 0 and a slope of 1. We're looking for where these lines intersect, and these lines intersect in an infinite number of places. So here we have infinitely many solutions. The equations are the same line. Both equations represent the same line. So, whereas in elementary algebra, we just said there are infinitely many solutions, our job in linear algebra is going to be to describe what the solution set. So to describe the solution set, we could just use one of the equations. I could just say y equals x minus 1 is the solution set. Everything that fits, every pair xy that fits this description is a solution to this system. So our goal is to describe the solution set. So our job is to describe the solution set. So we can do that in this case with an equation. Anytime we're looking at a linear system, these are the three things that could happen. No matter how many equations, no matter how many variables, three things could happen. One solution, 0 solutions, or infinitely many solutions. Geometrically, they'll be analogous to equations intersecting exactly once, graphs of equations not intersecting at all, or equations representing the same, well, in this case, line, but could be the same plane or the same three-dimensional thing, depending on how many variables we have running around. Notice that when we describe our solutions, when we're describing linear equations, we always describe them in the same way. So there's a starting point and a direction to go. Linear equations have that form. There's a start and then a direction. So a linear equation always has the form a linear equation always has the same kind of form. There's a starting point and a direction to go. And the direction is usually the one that's multiplied by some variable. In the case of y equals mx plus b, this is just y equals the start off at b and go in this m direction a bunch of times. Because that's what linear functions in two variables do. Y starts off at b and we add m a bunch of times. That's how we interpret the linear equation. There's some fixed starting value and then some direction to go. And the direction is what gets the variable. It's important to take a look at this format as start plus a direction. This is linear algebra. We're just going to take this linear equation, y equals b plus mx, and expand on it. B will be a point in three-dimensional space, and m could be a particular direction to make a line in three-dimensional space. Or there could be two directions, and a direction in the x, a change in the x direction and a change in the y direction, in which case we'll just have two different directions to go.
Can I ask a question?
Yes.
So when we want to describe the set of the solution set, if we write one of them, it's enough?
In this case, yeah, we just describe one of the equations. When there's more variables that are going to be involved, then we're going to need different techniques for describing a start plus a direction. But for this problem, we just have to pick one of the equations because both of the equations are equivalent to this y equals x minus 1.
Thank you.
Here's some terminology. When we get zero solutions, when a system leads to zero solutions, we say that the system is inconsistent. So this system with zero solutions is inconsistent. Inconsistent is a word that we apply to equations and systems of equations when there are no solutions. So inconsistent can be applied as a word that we can describe a system or an equation. If we have at least one solution, then we say that the system is consistent. So in this first example, we have exactly one solution. So that's enough to say that the system is consistent. And there is exactly one solution, so we'll say with a unique solution. That's the exactly one part. In the third example, we had infinitely many solutions, which means we had at least one. So this system is also consistent. But it's consistent with many solutions. So we got three cases. No solutions, we say the system is inconsistent. With at least one solution, we'll say that the system is consistent. And that will break down into two cases. where we have a consistent system with a unique solution or a consistent system with many solutions. Any questions? This will happen this whole class. And we're going to spend a lot of time coming up with how to write this description of the solution set to a linear system. And then we're just going to use that to interpret in various scenarios, interpret our solution set in various scenarios. All right, I'm going to pause the video here because this concludes 0, 1, or infinitely many. And then we'll go on to the next thing on the list, the augmented matrix. Glad I got that phone ring right in there at the end there.